morning, friends. I feel immense pleasure to be here for my course Aircraft Systems. Today I am in lecture number 31, and this topic of this lecture is modes of operation of fuel system. As you know, my name is Dr. Yagya Dutta Dwivedhi, professor from Institute of Aeronautical Engineering, Hyderabad, India. And as of now, I have covered the 30 lectures on this course. I have started with my module 1, which consists of airframe system, vehicle system, avionics system, and the mission system. In module 2, I have covered the electrical system, air conditioning system, environmental system, firefighting system, oxygen system, and so on. In module 3, I have covered the hydraulic system and the pneumatic system. In module 4, it is engine control and fuel control systems. I have covered the engine control system, which is electro-hydraulic control system, then full authority digital engine control system, and this is my lecture number 31, which I am going to discuss about modes of operation of fuel system. So here, these are my topics which I am going to take today. So first one is the fuel system of aircraft and in introduction. Single engine aircraft gasoline fuel system, multi-engine aircraft gasoline fuel system, turbine fuel system functions, refueling, defueling, and jettisoning. So fuel system for aircraft and introduction. This I am going to discuss about the fuel system. So an aircraft fuel systems allows the crew to pump, manage, and deliver aviation fuel to the propulsion system and auxiliary power unit of an aircraft. Fuel systems differ greatly due to different performance. So fuel systems differ greatly due to different performance of the aircraft in which they are installed. A single engine piston aircraft has a simple fuel system. A tanker such as KC-135, in addition to managing its own fuel, can also provide fuel to other aircraft. So this tanker aircraft has got huge amount of fuel. It is made to give the fuel to the other flying aircraft like KC-135. But if you have a small aircraft, it can only sustain for itself. Fuel is piped through fuel lines to a fuel control valve, usually known as the fuel selector valve. This valve serves several functions. The first function is to act as a fuel shut-off valve. This is required to provide the crew with a means to prevent fuel reaching the engine in case of an engine fire. The second function is to allow the pilot to choose which tanks feed the engine. Many aircraft have the left tank and the right tank selections available to the pilot. Single engine aircraft gasoline fuel system. So this is very simplest type of engine, and how these things are working, it is explained in this topic. The fuel level indication system in the simplest form in aircraft is a transparent window on the tank side, and in its usual application, a float-driven potentiometer installed in the tank. After the TWA Flight 800 disaster, a revision was made to aircraft fuel system to address the potential explosion hazard of electrical components located in the fuel tank. Single-engine piston aircraft fuel level system moves to utilize float level gauges from the CNG and the LPG industries, which had the float drive a magnetic coupling and relocated the potentiometer outside the fuel tank. As fuel is burnt, more air enters the tank and the capacitance increases. This is read by a computer and the fuel amount is calculated and displayed to the pilot. Recent advances in magnetoresistive technology have evolved new fuel level sensors for general aviation application. So this you can see here, a new, initially it was a float type, in that a resistance, it was like this. If fuel is here, a float is there, it will go up and down, and there is a resistance here. This resistance will indicate how much fuel is there. But this is not good idea, and some accident happened, and this is not used. Then they have started the capacitance type. So if the fuel is, capacitor is used, and if the fuel is here, and this air, how much is vacant, this, as the air is as the fuel burned, the more air is entered in this tank, the capacitance of this thing is increased. This is read by the computer of the fuel, and it is calculated and displayed by the pilot. So this is the another type of, but nowadays we use a magnetoresistive technology have been evolved for new fuel level sensors for general aviation application. So here we have the magnetoresistive level sensor, and this you can see here, by this magnetic, and the resistance of this thing will increase or decrease as per the level of the fuel. So this type of systems nowadays it is used for many of the aircrafts. Multi-engine aircraft fuel system. So adding tank and engine increases the complexity of the fuel system and its management. Additional features found in multi-engine aircrafts are: each wing tank often has its own electric boost fuel pump, and each engine has its own mechanical pump, replicating the fuel system described above for the single engine. In case of single engine operation, there is often a method incorporated to cross feed the engine, left tank feeding right engine or vice versa, or the right is feeding to the left tank. To balance asymmetric weight, flow valves and pumps often are used to feed both engines from one tank, or simply to transfer fuel between tanks. Turbine fuel systems. So if you see this turbine fuel system, to avoid water condensation on the fuel itself, solidifying at low temperature, that is minus 55 degrees centigrade, fuel tanks have a thermometer and heating system. Many are pressurized with engine bleed air to keep moist air out and ensure positive pressure feed to the pump. In larger aircraft, fuel tank also are in fuselage, and their load affects the center of gravity of the aircraft. This imposes limitation on the amount of fuel carried and the order in which fuel must be used. Turbine engines burn fuel faster than a reciprocating engine do, because fuel needs to be injected into a combustor. Because fuel needs to be injected to the combustor, the injection system of the turbine aircraft must provide fuel at higher pressure and flow compared to the piston engine. So in this, we need a very high pressure. High pressure is needed because in turbine, we don't use carburetor. In lieu, we use injectors to give a high pressure to the fuel. Okay, so Now fuel system functions. It is a fuel transfer, engine feed, fuel measurement, fuel management, and the fuel jettisoning. So these all things I will be discussing: engine feed, fuel measurement, fuel management, and the fuel jettisoning. So these are the 1, 2, 3, 4, and the 5. These are the 5 functions which a fuel system to perform. So here we have the operator and the design requirement. Here we have aircraft level requirement. Here we have airworthiness regulations. This all will come together and they will form at tank locations and the fuel storage requirement. Here we have the system functions, refuel and the defuel, engine and APU feed, fuel transfer and jettisoning, quantity measurement and indication, fuel management and control. Here this is the system functionality. Here we have the fluid mechanical functions. Then we have here pumps, valves and actuators, sensors, electronics and the softwares, avionics, sensors and the harnesses. These are the equipments which are used. Now I will talk about refueling and the defueling of the aircraft. Here airport-based ground refueling system is mostly done by help of the hydrant. Refueling prior to almost every flight is done. Time to refuel critical is also required. Backup gravity refueling is also done. Pressure refueling is also done. Quick aircraft turnaround time. Accurate load that matches upcoming flight. Extra weight of the unneeded fuel. Protection against overboard spillage. Protection against overpressurizing. Compatibility throughout the world. Compliances with CG limits. Residual fuel from previous flights. Here we have one ground fueling station, that is D1 nozzle. You can see how this is the aircraft and this is the hose. This hose is entering inside and it is by high pressure. This thing by the engine pump, it is operated and the refueling is done by the help of the ground bowser, which is supplied by the oil companies. Now we have the fuel system architecture, fuel entry point, high level sensors, balance tubes. If you see here, high level sensors are here. Then we have the here balance tube. This balance tube will balance the fuel. Here the rising fuel level. Here refuel shut-off valve, collector cells. Here also we have the rising fuel in the both the sides we have. So this is the example of the use of balance tube. So how this balance tube, this is the balance tube and here is also balance tube. This balance baffles check valves on semi-sealed ribs, initially inboard fuel tank and the collector cell fill first. So here collector cell will, this one will make sure that this one will be filled first. So like this very proper sequence of operation has to be followed. Refuel and transfer system. Refuel completely passive in flight. Refuel system combined with in-flight fuel transfer system. So if you see this diagram here, combined refuel and the transfer function. Here we have the transfer pump here, P. Then we have the refuel transfer shut-off valve. Then we have a common refueler transfer gallery. From here it will go to the common, and here is a ground refuel adapter. From here a ground truck which I have shown you here, this one. This pipe will enter in this point, and in this way refueling is done. Next I will talk about the failure modes. So what are the modes in which our fuel system may get failed? So shut-off valve. If the shut-off valve is, then a special venting configuration to prevent overpressurization. So one is the shut-off valve. Another one is special venting configuration to prevent overpressurization. So there is some venting system. So if it is overpressurization, the air will be going out and system will be pressurized and system will be held there. Pre-checks, shut off flow prior to reaching the selected fuel quantity. Refueling system design, refuel defuel requirements derived from top level aircraft configuration and operation requirement, use of electrical or fluid mechanical equipments. So these are the failures modes. So these are the preventive of the failure modes. So shut off valve is also, if any fire is there, we use the shut off valve. Any more pressure is there, then venting is there. We have to check the shut off valve from prior to reaching to the selected fuel level. So refueling system design, refuel defuel requirement derived from top level aircraft configuration and operational requirements, use of electrical or the fluid mechanical systems. Now defueling. Defueling means removing the fuel which is filled inside the aircraft tank. So how we can remove? Till now we have discussed that how we have to put in. That is called the fueling. Now it is called the defueling. Means it is already filled due to some reasons for the maintenance, for overall fueling in error, following an accident, refuel defuel point to allow access while uplanding, pressure or the suction defuel flow shut off. So in these type of occasions, defueling is done. Feed pump system, we have the boost fuel feed pump, we have the motor driven feed pump, we have the ejector feed pump. So these are the few feed pump system, and these are the some defueling methods in which we do the defueling of the aircraft. Engine and APU feed. APU is auxiliary power unit. So how this APU is getting feed from the engine? So electrical power when aircraft on the ground, additional electrical power in flight, engine driven generator inoperative, air conditioning on the ground, air turbine starter. Then we have to start the APU. How to start? Fuel pump. We have to use the fuel pump. Feed tank and the engine location. Each engine has its dedicated feed tank. Aircraft with rear mounted engines, long feed lines, large variation in fuel pressure at engine interface. So these are the things which we have to use. So now it is continuation of this. We should have high volume flow. We should have the high volume flow, low pressure and high reliability of the system, mounted on the lower boundary of the feed tank, easy removal without drain the tank, a spar mounted pump, performance penalty, ability to operate with air or vapor at inlet or no inlet feed fuel head, rotor failure condition, motor winding over temperature. Fresh kerosene can contain 40% of the air by volume at sea level. Air climb, air bubbles out. So if it is 14% of the air, ATFK can absorb. So if it is climbing very fast, so this air will make the bubble and it is not good for the burning of the system. So operating condition approaching fuel vapor pressure. Here we have the motor driven fuel pump schematic. So this you can see here that how the fuel pump is working. So here we have the centrifugal pump element. It is and fuel is entering from here and it is going out, and this will give, here is a motor, and this motor will give the pressurization of this system. So here this is the same here, and so here it is inlet, here also inlet. This will go here. From here it will go to the outlet, and this pressure of the system will increase. Here we have the poke open vent valve. It is for the vent. Here we have the canister. Here we have the cartridge. Here we have the electrical connector for the motor operation. Here the pumping elements and the motor. So these are the pressure switch and check valve. So these are a simple motor driven fuel pump is shown for the this purpose. Here we can see further that pressure rise of this pump and mass flow. As mass flow is here, 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 here. So increasing altitude, as the altitude is increasing, the mass flow rate is decreasing. So this is altitude, the high altitude, mass flow rate is less, and it is a low altitude, mass flow rate is more. So it is inversely proportional to the altitude of the aircraft. So feed system block diagram, it is shown here that here we have the Mach number sensor, operating altitude, vent pressure recovery. From here it goes to the feed pump characteristics. This you can see here, it is shown here. As per this characteristics, pressure and the mass flow rate, and this will give the correction here. Pump outlet pressure here, then it will go to the feed line losses and engine inlet. Here it will go to the engine, and here it will burning of this will take place, and the system will operate in this way. Now I am going to discuss about the ejector pump. The ejector pumps, smaller aircraft, no moving parts, high pressure motives, flow source from the engine, separate motor driven pumps, and for starting, dedicated pump on engine gearbox, outlet, and the fuel pump. Low efficiency, it is 30% efficiency of this type of systems are observed. Ejector feed schematic I have shown here. This is the schematic of this thing, and here this you can see the ejector, how this, it is a converging, this diverging nozzle here, and fuel is coming here. Aircraft feed tank, here feed ejector pump is here, and here if you see we have the motive pump here, we have here backing pump, high pressure stage, bypass flow pump, fuel metering unit, and then it goes to the engine. Feed tank scavenging. Scavenging pumps do to suck up fuel from the remote corners. Scavenging ejectors are used. Water contamination can be significant. Time between flight and insufficient for water to settle out. Scavenging pump break down water into small droplets. The pump engine. Negative G consideration. So when we have to see that it is a negative G, fuel will migrate towards the upper surface. Pump capable of separating out air at inlet. Collector cell kept full and slight pressurized. These are the feedback system diagram. I am not going to explain much about this, just only for your knowledge. So here feed system design, we have the critical function, hard fuel operation, hard fuel climb, fuel type, fuel vapor pressurization. And if you talk about the design requirements, keep fuel velocity 10 feet per second should be there. Feed line should be very much smooth. Thermal relief, excessive pressure if all valves closes, trapping fuel. Air release valve to separate air from the fuel. It is a failure. Fuel transfer, fuel consumed from various tanks with predetermined schedule, fuel burn sequence. So it is a CG, wing load, and the tank quantities. Then it should be controlled by the crew, by the automated management system. Fuel burn scheduling, twin engine with 2 tanks, cross feed in event of an engine failure, plus lateral balancing. System design requirements, we have the motor operated valve, solenoid operated valve, accommodation of the failure, fuel will not be trapped, redundancy of the functions, backup gravity transfer, valve fails to preferred position. Fuel jettisoning, it is removing of the fuel from the emergency. So maximum takeoff weight, if it is increased, that time we do this thing. Maximum landing weight, if it is increased, we do this. Emergency situation, takeoff need for a soon as possible landing, 30 to 45 minutes. We have to carry out. Jettisoning system example, allow jettisoning to proceed while engine feed supported. Crew workload kept to minimum to focus to the initial emergency condition. Fuel quantity, how to measure the fuel quantity? Measure the fuel contained in all tanks, information to both the flight deck and the refuel panel. Mass quantity stored energy, variation in fuel properties, stratification, warm fuel or the cold residual fuel, variation in fuel surface due to the maneuvering, tank distortion, unusual ungaseable fuel, integrity reasons, volumetric information dependence of the primary system, high level sensing, overfilling and capacitance sensor part of concentric tube permittive difference. So fuel load planning, we have to see that how the fuel is loaded, critical or the long range, weather wind forecasting, 5% margin for the inaccuracies, additional fuel to allow diversion to alternate airfield, additional fuel to allow 30 minutes flying after reaching the alternate field. Leak detection also we have to carry out, fuel management and the control we have to take, refuel accuracy, and I am just, next topic will be my fuel tank safety. These are the references which I am going to take, and any questions you are welcome to ask. Thank you very much for this joining. If you have any question, please reply me to this mail. Okay, so just I am ending here. Thank you very much for joining my class.
Like, share and subscribe. Hit the bell icon for more updates.